Because we believe in protecting freedom, we build the fighters that will. Because we believe in bringing help to the hurt, we build the helicopters that will. Because we believe in bringing families together, we build the airplanes that will. This is the world we will leave to our children. We must make it with the best of our skill. And because we are the people of McDonnell Douglas, McDonnell Douglas will.
Hello, I'm Gene Adam with Innovations, a look at how we develop and apply new technology throughout McDonnell Douglas. How do you most effectively control the flight of an airplane? 93 years after the Wright brothers' history-making flights, aerodynamicists are still asking the same question. Wilbur and Orville steered their flying machine with an elevator in front to make it go up and down, and a rudder in the back to make it go left and right. They also devised a system of wires that twisted and warped the wing, making it act like one large aileron to control bank angle. Aerodynamicists abandoned the Wright brothers' flexible wing, preferring a rigid wing with hinged ailerons on the trailing edge. Ailerons, rudders, and elevators are controlled by cables and pulleys attached to a control stick and rudder pedals in the cockpit. The pilot used muscle power to move the control surfaces. But with larger and faster airplanes, especially jets, the increased air pressure loads on the control surfaces made them unmanageable by muscle power alone. That's when hydraulic boost control systems came along. Through a maze of pumps, valves, and tubing, high-pressure oil is sent to hydraulic actuators attached to the control surfaces. As you can see in this hydraulic system mock-up, an assembly of cables, pulleys, and push rods control valves in the actuators to move the control surfaces. It's like adding power steering to an automobile. Meanwhile, in the military world, combat fighters were being designed to be more maneuverable. That led to aircraft that were less aerodynamically stable. Some system was needed to help the pilot fly the airplane, to take advantage of its newfound agility. Fortunately, another technology was rapidly advancing: computers, and our engineers quickly put them to work. An analog computer was used in a stability augmentation system aboard the F-4 Phantom to smooth out its flight, much like shock absorbers. As smaller, more powerful digital computers arrived, all kinds of possibilities opened up. Hooked up to sensors that monitor an aircraft's motion and pilot inputs, computers can instantly orchestrate the best position for control surfaces to optimize the airplane's handling. And because computers are electronic, why not replace the mechanical linkages to actuators with wire? A fly-by-wire system is lighter and provides redundant control circuits for better survivability. The F-15 Eagle has a combination electronic and mechanical control system. The F-18 Hornet is full-time fly-by-wire, but with mechanical backup systems. And the C-17 Globemaster III is the first fly-by-wire U.S. transport. The new Super Hornet is a pure fly-by-wire airplane. Its high performance is totally dependent on its digital flight control system. At the Phantom Works here in St. Louis, engineers are using neural network and fuzzy logic technology to design even more intelligent flight control systems. They're developing a damage adaptive system that detects in-flight battle damage, hydraulic loss, or control surface failures. Computers diagnose the failure and instantly reconfigure the flight control or propulsion systems to restore control to the pilot. We're planning to use these self-repairing systems on the C-17, and we've demonstrated the technology on an F-15 and a commercial jetliner. This MD-11 is landing without hydraulic flight controls. No flaps, no rudder, no elevators. Only engine thrust controls the direction of the airplane. The successor to fly-by-wire will be fly-by-light. Lighter weight, multi-channel fiber optic lines, much like these, will carry control signals to actuators that have their own self-contained electrically powered hydraulics. Now we can consider replacing central hydraulic systems with more efficient power-by-wire systems. The past 93 years have seen an amazing evolution in flight control surfaces themselves. We've added slats, flaps, tabs, spoilers, stabilators, and even thrust vectoring. And we're about ready to add another. It's called an aeroelastic wing, and it's especially adaptable to fighters with thin wings like the F-18C and D. The idea is to improve the harness ability to roll at supersonic speeds. The leading edge flap on the wingtip will be extended into the airstream. That causes the entire wing to twist or warp, turning it into a control surface, like one large aileron. Sounds familiar, doesn't it? Back to the Wright brothers. With innovations, I'm Gene Adam.
Thanks, Gene. That's it for this edition. I'm Donna Race. From all of us at Flight Times TV, thanks for watching.